raise an important question that I want to comment on, because some of you may be familiar with the fact it is well known that if d equals 4, higher point integrals can be reduced using tensor reduction techniques to boxes or lower point. Okay, so if you're coming from that school of thought, you would ask, why on earth do I have this pentagon? Well, it's only slightly less well known that this holds only modulo terms of order 4 minus d. So in other words, there's an integral relation which goes back to a paper by Byrne-Dixon and Kosower, which says that the integral of so I have in mind now viewing this as a rational function, and if you integrate that dBL, this is equal to or proportional to a cyclic sum of boxes of that form plus order 4 minus d. So if the only, and I should put an equal sign. So if in your particular application you're content with working in dimensional regularization, and if it's sufficient for your purposes to ignore terms that integrate to 0 in precisely 4 dimensions, then it is possible to take this expression and rewrite it only in terms of boxes. So the reason I'm making this point is that when we talk about constructing integrands, depending on exactly what the application is that you have in mind, you have to be really careful whether you are trying to construct an integrand that gives you point by point in loop momentum space the exact expression that you would get from a sum over Feynman diagrams, in the case when that's even well defined. Or if you have an integrand that may differ from the sum over Feynman diagrams by some terms that integrate to 0 in d dimensions, or an even weaker criterion, an integrand that differs from the official field theory integrand by terms that integrate to 0 in exactly 4 dimensions. So it's important to distinguish those concepts. In n equals Fourier-Mills theory, we often like to stick with the strongest form of the word integrand, which means the actual value of the sum of planar Feynman diagrams, point by point in loop momentum space. Now, next topic I want to introduce is a very important topic called momentum twistors. And we're going to actually revisit some of these calculations in momentum twistor space, and it will be crucial for you to know this not only for my lecture, my next lecture tomorrow, but also for Nima's lecture. So I think the best question to motivate momentum twistors is to ask how best to parameterize the kinematic domain. In other words, if we're talking about an n-particle scattering, and without loss of generality, we view our momentum to be complex, well, each momentum is a 4-component vector, so we have 4 n complex numbers subject to 2 constraints. Each one should be null, and they should sum to 0. Now, it's a headache to work with constrained variables, in large part because, let's say you've done some enormously tedious calculation and you get a 50-page Mathematica file for your answer, and your graduate student does the same tedious calculation but made some different choice how to arrange terms or something, and they get a different 50-page Mathematica file. How on earth are you going to tell whether or not the two things are equal if you're using variables that are subject to constraints? So what we'd like to have is a set of variables that freely parameterize this kinematic domain. We saw in the lecture yesterday that this can be taken care of by going to spinor helicity variables. But even in spinor helicity variables, you still have a quadratic constraint on your spinor helicity variables coming from overall momentum conservation. So the idea is the following. Since the sum of the pi is equal to 0, you could imagine drawing them one after another. Okay, so each of these line segments represents a null line segment in the Minkowski space. And if you put your n momenta back to back, they have to form a closed polygon because they sum to 0. So we can define, let xi be the location of the vertices in this diagram. So this will be x1, x2, x3. Now, of course, there's an overall translational degree of freedom because there's nothing yet that specifies where the origin should be in this x space. So just pick some origin for the moment and then define all your x's in this way. So specifically, we define the x's by this relation. Okay. Now using pi equals lambda I tilde. And by the way, in what follows, I'm going to switch back and forth, and it's important that you be able to do this in your head as well. I switch back and forth between thinking about this as a 4-component vector with index mu, or thinking about this as a 2x2 matrix with indices alpha and alpha A and A dot. And similarly, the x's you should think of either as a 4-vector or as a 2x2 matrix, depending on the context. So in order to save index space, in order to save chalk, here I'm just writing this as you would in the 2x2 matrix notation. So what we can do is take that equation there at the bottom, which defines pi, and we can take the inner product of both sides with lambda I. So if you allow me to put the indices back, remember that they contract with the epsilon tensor. So on the left-hand side, lambda I is repeated, you're going to get 0. So I'll just write this for simplicity like this. Okay, once again, the way to think about this is a 2-component vector. So that's a 2x2 matrix acting on a 2-component column vector. The result is, again, a 2-component object, so with an A dot index. So since these two things are equal to each other, let me give them a name. UIA dot. Then we combine lambda and mu into the 4-component object Ci Now, the important thing about this is that it's naturally a homogeneous coordinate of a point in P3. Now, why is that? Remember, if you go back to the Spinner-Helissi variables, it's clear that if you scale lambda and lambda tilde by inverse non-zero complex numbers, then you leave your P unchanged. And you naturally leave the X's unchanged as well. But from this equation, it's clear that under such a scaling, lambda and mu transform in the same way. So here you've got a four-component object with the property, and this will become a little more clear in the next few manipulations, with the property that if you scale all four components by any non-zero complex number, then the physical kinematic configuration is unchanged. So these are naturally points in P3. Okay. So the idea behind momentum twisters is that there is a correspondence where a line, a null line in Minkowski space, or X space, corresponds to a point Z in P3. That's what we've seen here. And conversely, a line in P3 corresponds to, well, let's see what it corresponds to. Suppose you give me 2 points, Zi minus 1 and Zi in P3. Okay, so these are 2 points in P3. And I can consider them to define a line, naturally. Well, notice that we can then look at these equations here, which are called the incidence relations. This equation right here. Note that mu I is equal to xi lambda I, but also mu I is equal to xi minus 1 lambda. So in order to see that, you have to use this incidency relation twice, once for the point Zi and once for the point Zi minus 1. So the point is that the same pair participates in 2 incidence relations. So now subtract both sides. We find that 0 is equal to xi minus x minus 1 lambda I. Now the only way this equation could be true, so remember again, this is a 2 by 2 matrix. That's a 2-component column vector. The only way that this can be true is that this 2 by 2 matrix must have determinant 0. Or in other words, xi minus 1 is null. So the correspondence between Minkowski space and this momentum twister space P3 looks like the following. Anytime you have a pair of points that are null separated, this corresponds to a point, Pi in P3. And anytime you have an arbitrary line in P3 that's prescribed by 2 points, there is a corresponding point, xi in Minkowski space. So I've now deleted the question I've asked, but the answer is simply the following. The zi are free variables in the following sense. Pick any ordered, of course it's implicit here that I have made crucial use of a cyclic ordering on my points, which is appropriate, for example, when you're talking about a planar gauge theory. Pick any ordered points, z1 to zn, in P3. They can be anything you want. And then you draw the line between each point and its cyclic neighbor. Each line, I'm not going to write it again since I've already written it. Each of these lines corresponds to a point in Minkowski space. So this line corresponds to the point x1. No, in my convention, this is x2, x1, x3, etc. So over here in Minkowski space, we have x1, x2, x3, x4. And the point is that these are all guaranteed to be null separated as a consequence of this construction. So this line here corresponds to Z2, Z3. So the point is that these momentum twister variables provide a free parameterization of the kinematic domain. And that makes them incredibly useful for a number of purposes. I do have 10 minutes left, so let's quickly review. Well, the last thing I want to do is revisit our computations of leading singularities from earlier in the lecture, but now using momentum twister variables.
Do you want to use the explicit formula for black that you want to tilted?
I could.
Oh.
Yeah. Yeah. You can invert this. You can invert this to write an explicit formula. Okay. Since you asked. To pave the ground for your talk.
I'm not going to use it.
You're not going to use it.
No, but just
yeah.
so you see how magical it is.
Yeah. I hope this is right. You can invert this construction and, right, so the point is, if you pick an arbitrary collection of z's, remember that I have decomposed z into lambda I comma mu I. So if you give me n arbitrary points in P3, if you invert this construction, you can check that the lambda tilde associated with a given momentum twister zi is given by this formula in terms of the mu coordinate of it and its two cyclic neighbors. So yeah, it's really awesome. I mean, it's difficult to overstate the importance that this construction has had on our field. So the last thing I want to discuss is momentum twister loop integrals. So let's revisit our scalar diagram that we've talked about a lot. What you can do is change variables to X space, and you can write this in the following way. X space, you're introducing variables for each face of this diagram. Remember the relations I've now deleted that tells you that pi is given by xi minus xi plus 1. So this face is naturally associated with x2, that with x3, x4, x1. And then each loop integration face is associated with some variable that you have to integrate over. Now what we'd like to do is to translate this into momentum twister space. So how do we write loop integrals in momentum twister space? In momentum twister space, I'll just write in P3, the point x corresponds to some line. In order to specify a line, we need to specify 2 points in momentum twister space. Let's call them A and B. So anytime we see an integral d4x, that should correspond, and I'll first write roughly, and then we'll figure out exactly. This should correspond roughly to an integral over the points, 2 points A and B, that specify the line. So the idea here is instead of integrating over all points in Minkowski space, we can integrate over lines in P3. And the line can be characterized by 2 points that lie on it. But of course, this can't be the right answer. It's not even projective invariant. And moreover, we need to make sure that we're actually integrating only over the line that contains A and B, not over A and B separate. So the right way to do the change of variables involves a few additional factors here. And then a volume of GL2. This factor, we'll see how this plays out. Well, I probably won't have time, but the basic idea is you need to mod out by GL2 transformations that move A and B around, but don't change the line that they define. Right? If you let ZA prime and ZB prime be some GL2 transformation on ZA and ZB, then these 2 variables define the same line as those 2. So you don't want to overcount in your integral. So, example, this scalar integral you put all the factors. Remember that this was the one loop 4-particle amplitude. In Super-Yang-Mills theory. And it can be represented in momentum twister variables as this simple integral where the bracket represents the SL2 invariant inner product of 4 homogeneous coordinates in P3. Or specifically, if you view each of these as a 4-component column vector, then you just put them next to each other and take the determinant. Let's revisit in the last 2 minutes the question of finding leading singularities.
Define the 2 brackets.
Oh, yeah, thanks. Here, this is a vestige. Here I literally mean that this is the ordinary spinor helicity 2 bracket for the first 2 components of ZA and the first 2 components of ZB. So that the view, if you will, the lambda associated with ZA and the lambda associated with ZB. Yeah, so ZA is lambda A, comma mu A, where this is 2 components and that's 2 components out of the 4. And So this literally means the spinner bracket, lambda A, comma lambda. These kind of factors always drop out at the end when you have nice dual conformity variant. So here's the integrand. This is the rational function we call the integrand in momentum twistor space. So last time when we visited this calculation of looking at the leading singularities of this integral, I just wrote the answer for you. I claimed that there are two leading singularities at 2 points L1 and L2. And I wrote the formula for you, and we checked that they were correct. But here, in these variables, it's actually quite easy to see. If we want all four of these propagators to simultaneously vanish, what that's telling us, so all four pops vanish, if the line AB intersects four other lines, the line 1, 2, 2, 3, 3, 4, 4, 1. So in P3, here's our external data. This is the line 1, 2. This is the line 2, 3. This is the line 3, 4. And this is the loops. With a little editing, that's line 4, 1. Now, how can we pick a fifth line, AB, so that it intersects all four of those lines simultaneously? Oh, I'm colored shocked, and I only realized in the last minute of my lecture. How's that? There are obviously two solutions. That's one way to draw a line that passes through all four of those lines. This is the solution AB equals 1, 3. But there's another solution, AB equals 2, 4. If you did the exercise of translating these momentum twistor variables back into momentum space variables, you would see that this gives us the locations L1 and L2 of the leading singularities we found previously. The very last thing I want to do is look at the one loop 5 particle amplitude. Which involves well, in particular, it involves this kind of thing. Oops. This is one of the contributions we looked at before. Here, the propagators are, if this space corresponds to AB in momentum twistor space, then my propagators are AB1, 2, AB2, 3, AB3, 4, and AB5, 1. Right. This space is 1, 2, this space is 2, 3, this space is 3, 4, and that space is 5, 1. So again, we have a geometry problem. If this is Z1, Z2, Z3, Z4, and Z5 in momentum twistor space, then these four lines are 1, 2, 2, 3, 3, 4, and 4, 5.